In the previous lectures, we studied linear functionals, and in particular we studied the set of all bounded linear functionals on some normed space. And we call this space of bounded linear functionals a dual space. So today we will further bring our analysis and we will speak about the second dual. So first of all, let us take X to be a normed linear space. As a consequence of Hahn-Banach theorem, we know that on X there is always non-trivial bounded linear function. The space X star, the dual space, is non-empty. And we also know that this X star is a normed linear space in its turn. So since it's a normed linear space, we can consider bounded linear functionals on this space. So we can consider the space X double star, which is the dual of the dual. And we know that it's non-empty, it's a normed linear space, so we can consider the bounded linear functionals on this second dual to get the third dual, and so on. So let me write that we call this space second dual. Let us go further with a lemma. Let us fix a point from the space X. So throughout the lecture, X is a normed linear space. Let us fix a point from the space and consider mapping capital F sub X from its dual to the set of scalars. And we define it is a mapping on the second dual. So the arguments of this mapping are linear functionals. So the value of this mapping at a linear functional f will be the value of f at the point x. So it's just an evaluation function. So the value at f is just f evaluated at this point x. So we claim that this mapping is a bounded linear functional on x star. So it belongs to the second dual. So it's a bounded linear functional on x star. And moreover, the norm of this functional equals to the norm of x. Well, first of all, the linearity is pretty much straightforward. So the linearity is an exercise for you. So let us show that it is bounded. The value of this capital F sub x at little f, well, it equals to just, it's not a norm, it's an absolute value, just equals to f of x, which is, by the definition of the norm of this little f, which is a bounded linear functional, can be estimated by the norm of f times the norm of x. And this estimate tells us that the functional f sub x is a bounded functional. So it is, and its norm bounded by the norm of x. the norm of f sub x less than or equal to the norm of x. To prove the converse inequality, we will use one of the corollary of the Hahn-Banach theorem, where we prove a norm of an element can be computed through the values of all possible functionals on this element. We know that the norm of x equals to supremum absolute value of f of x over all bounded linear functionals of norm 1. By definition of f sub x, we have that it's a supremum of f sub x of f over the norm of all f from of norm 1. But again, by definition of the norm, this is nothing but the norm of f sub x. And we're done. So in this lemma, we have defined a bounded linear functional on x star. So using this functional, we now define a mapping from x to its second dual. So let us consider a mapping J sub capital X from x to its second dual given by J sub x of x, where x is a point from capital X, equals to capital F sub x for every x. I will use this fancy way of writing capital X to distinguish the little x and the capital X. Or, in other words, J sub x of x at a point f equals to f sub x at a point f and equals to f of x for every x from capital X and f from the U. As a corollary of the lemma which we have just proved, we have that this mapping is an isometry from X into some subspace of or subset of the dual. Let us first note that this J sub X is a linear operator. That's fairly straightforward from the definition. And as a corollary of the previous lemma, we have that J sub X is an isometry. It's nice to have an isometry, but it's much nicer to have an isometric isomorphism, because in this case we can identify the space X and its second dual, which is much nicer property. So, and it is in fact a very nice property, so it deserves a special name. Definition. A space X a non-linear space, is said to be reflexive if J sub x from x to its second dual is an isometric isomorphism. So it's not difficult to prove that this operator J sub x is one-to-one. So it's not difficult to prove this. So the only question is whether it's onto the second dual or not. Remark. X is reflexive if for any functional, or rather point, from the second dual there exists a point from the original space such that J sub x of x equals to phi, which is nothing but stating that the mapping J sub x is onto the second dual. Or phi is an element from the second dual, so it is a functional on the first dual. It acts on the functionals from the first dual. So this equation, this identity, means that phi of f equals to J sub x of x of f, which is, by that formula, equals to f of x for any f from the U. Again, x is reflexive if any element from the second dual is of this form, so its value at a point f equals to the value of this f at some point x from the original space. Let us consider examples. Let us start with a very simple example. Let us start with a Hilbert space. Recently we have proved that any Hilbert space is isometrically isomorphic to its dual. And so the second dual of H is isometrically isomorphic to its first dual, isometrically isomorphic to H, which means that any Hilbert space is reflexive. Let us consider the second, not very complicated example. Let us take the finite-dimensional space. Let E be a linear space such that the dimension of E is, say, M, and let us consider the space E with the infinity norm, with the maximum norm. Let us now fix an element y from this space and consider a linear functional. It is easy to see that this functional is linear. Let us prove that it is bounded and compute its norm. The absolute value of f of x equals to the absolute value of this sum. Using the triangle inequality, I can write it as the sum of absolute values and now I will estimate each xk by its norm. this second expression is nothing but the norm of x. So in particular, the norm of f is less than or equal to this sum. Let us now prove the inverse inequality, so to prove that the norm of f equals to this expression. So first of all, for every x, we have x equals to xk times ek, where ek is a basis of E. Now, I will apply the linear functional f to both of these inequalities. And by linearity, I can write it as this. And so, the elements yk equals to f of ek. Let us now consider an element x naught equals to the sum of sine of yk times ek. It is easy to see that the norm of this x naught equals to 1. So it's a maximum norm. On the other hand, we have that f of x naught equals to sine of yk times f of ek, but f of ek equals to yk. So what we have over here, we have yk times the sine of yk, which is nothing but the absolute value of yk. This proves that the norm of f, in fact, equals to this expression. So what we proved, in particular, is that there is a one-to-one correspondence between the bounded linear functionals on E and elements of E, and this correspondence is non-preserving. But we started with E equipped with the infinity norm. But the norm of the bounded linear functional equals to the one norm of this element y. So in particular, if we consider Rm with infinity norm, then its dual is Rm with one norm. And its second dual is again Rm with infinity norm. So this space is reflexive. In a similar fashion, it can be proved that the dual of L1 is L infinity. That will be an exercise for you. But here we should be careful because the dual of L infinity is not L1. We will discuss it a little bit later. Let us now compute the dual of LP. Let y be an element from LP, P between 1 and infinity. We have discussed in previous lectures that the functional f of x equals to an infinite sum of xk, yk, that this functional is linear and bounded on LP. And moreover, the norm of this functional, is less than the norm of y in LQ, where 1 over p plus 1 over q equals to 1, so they are conjugate. So what is written here? We already know that any point from LQ generates a functional on, yeah, this is nice. Yeah, so, yeah, it should be Q. It should be Q over here. And this is a linear and bounded on LP. So what we've written here is that any point from LQ generates a functional on LP. Let's consider the converse situation. Let us take any functional on LP and see that it is in fact generated by the point from LQ. So let f be a bounded linear functional on LP. And let us take EK to be an orthonormal basis for LP. Well, where EK has all coordinates being 0 except the kth coordinate. Zeros everywhere except one at the kth place. Any element x from LP can be written as a linear combination of the basis vectors. Then we apply a linear functional to it. So let us take an element from LP. We have that we apply f to x, and by linearity we obtain that it equals to the sum of xk times f of ek. So let us set, for simplicity, let us call all these elements f of ek, all these numbers f of ek. Let us call them yk. So what we want to show now is that the sequence yk belongs to LQ. So let us fix a number n and well, q greater than 1 such that 1 on p plus 1 on q is 1. Let us consider specific sequences. So let us define xn, it's not a power, it's just a notation, to be absolute value of yk to the power of q minus 1, then sine of yk times ek, k from 1 to n. Well, q is greater than 1, so q minus 1 is greater than 0. And also let us note that for any n, xn is just a linear combination of n basis vectors, which means that it belongs to LP. So let me now apply the functional f to both sides of this formula. Well, f is a linear functional. So what I get here is yk to q minus 1 sine of yk. And over here it is f of ek, which is, as we have seen, is yk. So what do we have here? Yk times sine of yk, which is the absolute value of yk. And over here we have absolute value of yk to q minus 1. So what we get is absolute value of yk to the power of q. On the other hand, we can estimate the value of f at xn from above by the norm of f times the norm of xn in LP. We know that every xn is in LP, which is, by the definition of the norm, equals to the norm of f times sum to the power of p xn up to infinity 1 over p. So this is xn and this is its case coordinate. Well, technically speaking, up to n, because after that they're all zeros. So let's go up to n. It equals 2. So the coordinates of xn are nothing but these numbers, the coefficients of ek. So when we take the absolute value, this sign disappears, and what we are left with is yk to the power of q minus 1 to the power of times p, 1 over p. Having p and q conjugated, we can deduce that q minus 1 times p, q minus 1 times p is q. So over here we use that q minus 1 times p is q. It equals to then the norm of f times yk to the power of q, 1 over p. We have proved this inequality for the value of f at xn, but it equals to this expression. So what we proved is that this sum is less than or equal to the norm of f That's what we have, which holds for any n from n. Let me now divide it through by this expression on the right, assuming that it's not 0. If it's 0, then everything is trivial. And then I get the norm of f is greater than or equal to this sum yk to the power of q, and then this above index will be 1 minus 1 over p, which is 1 over q. And this again, this estimate holds for every n. So I can take a limit when n tends to infinity. That the norm of f is greater than or equal to the infinite sum which is nothing but the norm of y in LQ. And in particular, y belongs to LQ. So, we have established an isomorphism between the functionals, bounded linear functionals, on LP and the elements of LQ. And moreover, through this proof, we proved that the norm of f equals to the norm of y. So what we've done, in fact, we established an isometric isomorphism. The dual of LP is isometrically isomorphic to LQ. where P and Q are conjugate. In particular, the second dual of LP is isomorphic to the dual of LQ is isomorphic to LP. So LP is reflexive for any P strictly between 1 and infinity. Well, there are interesting cases left here. So the case of L1 and the case of L infinity, which I excluded from here. Let's now consider the case of P equal to 1. We know from the exercise, which I gave you, that the dual of L1 is L infinity. So if the dual of L infinity L1, then it is reflexive. So exercise L1 is a subset of dual of L infinity. And I will give you hints how to prove this. 2 lectures ago, when we discussed the first applications of Hahn-Banach theorem, we in particular discussed the extended limits. And that extended limits will be the crucial point in this proof. So take f from L infinity to be an extended limit. And then prove that there is no element from L1 such that the mapping J sub L1, there is no element X. No element X such that J sub L1 of X equals to G equals to F. And a further hint to how to prove this will be the property of extended limits. So, well, it's not, it follows directly from the name that extended limits extend limits. The limit, the usual limit functional. So let me further hint on the fact that for every x from C0, and in particular for every x from L1, and extended limit and an extended limit f, we have f of x equals to 0. Since extended limit extend the usual limit. Let us prove a very nice property of reflexivity, which will tell us that a space is reflexive if and only if its dual is reflexive. And before we start the proof of this theorem, it will be convenient for us to have the definition of the mapping J sub X in front of our eyes. So let me recall. Recall that. the mapping J sub x from x to its second dual given by J sub x of f equals to f of x. So let us suppose that x is reflexive. So we want to show that x star is reflexive. Or, equivalently, that. So now the mapping J acts from x star to x triple star. So we want to, or equivalently, we want to show that for any element rho from x triple star, the third dual, there exists an element f from the first dual such that J sub x star of f equals to rho. That in fact the statement that J sub x star is onto this third dual. So let us take an arbitrary element rho from the third dual. And let us just say that it's an element from the third dual, so it is a linear functional on the second dual. So note that rho is a functional from the second dual to the set of scalars. And let us also note that J sub x is a mapping from x to the second dual. So the functional rho composed with J sub x is a functional from x. J sub x maps it to x double star, and rho maps x double star into f. And it's also not difficult to see that this functional is a bounded linear functional. It belongs to x star. So it's a functional on x. Let me call this functional f. And what we want to show, in fact, that J sub x star of f equals to rho for this specific f. Both of these expressions are the functionals on the second dual. So equivalently, we want to show that these functionals coincide on any point from the second dual. Let us now use the fact that x is reflexive. Since it's reflexive, for any point from the second dual there exists a point from the space X itself such that J sub X of X equals to phi. With this in hand, let us prove this equality. So let's start with the left-hand side. By definition of the functional J sub whatever space, it acts as evaluation. So this functional is nothing but the evaluation of these at this point. But just over here, we wrote phi as J sub capital X of X. So let me just plug it over here. Just replaced phi by this expression since they equal to each other. Now, by definition of the mapping J sub X, this is nothing but f of X. By definition, f is nothing but this composition. But how does the composition work? So we take an input X, first apply this component to X, and then apply rho. So this is nothing but rho of J sub X at X. But this is phi. And we are done. So X star is reflexive. Let us now prove the converse. Let us suppose that X star is reflexive. And let us suppose to the contrary that X is not. Which means that the mapping J sub X is not onto. That is, there exists a point omega from the second dual set minus J sub X of capital X. So that's a set. The whole image of X under the mapping J sub X. So it's not onto, there is a point from the second dual which does not belong to the image of this mapping. But X itself is a non-linear space. As a space, it is closed. The mapping J sub X is bounded or continuous. So continuous mapping of a closed set is closed. So we have a closed set and a point which does not belong to this set. So we can apply this separation theorem. Then it follows from the Hahn-Banach theorem that there exists a functional on the second dual, which means that it's an element of the third dual, rho from the third dual such that the value of rho at that point omega is 1, but this functional rho vanish on this space. Equals to 0 for every little x from the big X. Now let's exploit the reflexivity of X star. So since X star, the dual, is reflexive, then for every rho from the third dual, there exists an element F from the dual such that rho equals to J sub X star of F. So we have f of x equals to J sub capital F x at x at the point F by definition of this function. How does this mapping J works? So if we have f of x, then we just swap them around and apply J over here. What I'm going to do here, I will swap these and apply corresponding J to F. So it is J sub X star of F of J sub X of X. So I just swap them and apply J. But this one is nothing but rho. And by construction, rho on this expression is 0 for every x from x, which means that the function f is identically 0, so it's 0 everywhere. On the other hand, rho of omega equals to, by definition of rho, not by definition, by this formula, of f of omega, which works as evaluation, which is omega of f, and omega is a linear functional, f is 0, so it is 0, and we obtain the contradiction. And we're done.